My name is Michael Pace, the president of Building Resource. We're an independent manufacturer's agent, so we work for a number of manufacturers doing their architectural promotion to the design community, the construction community, and owners as well. And I'm a CET, civil, out of Mohawk College, and a BSSO, Building Science Specialist, Ontario, since 2008. And I've worked in Canada and the US for about the last 25 years. Companies, if you've been around a while, you might know Sternson, way back, Harris Specialty Chemicals, which is now BASF, and Georgia Pacific, and a few other places along the way. I actually was the chairman of Construct Canada for 3 years as well, back in 1999 to 2002. So thank you for coming. I hope you enjoy the presentation. So we have a couple of formatting issues, apparently. That's supposed to go right across the slide, so hopefully everything will work out here. So as I said, we are a solution provider. We try and put together systems for specifiers, and we deal with the design, construction, and site service, the whole range of things, right from the beginning to the end. And I highlight that we're not a code or building consultant. So we're going to talk about some concepts that are tried and true and that you're familiar with, and maybe some things that are new. And if you're considering using any of these things, you know, you can ask me any question you like, but keep in mind that you still need to talk to your building consultants. So these are the partners that we deal with: BASF Wall-Tite, Atlas Polyiso, SRP Canada, ChemLink, which is polyether polymer chemistry, Lido prefabricated wall systems, and 10 plus louvers and sunshades. So just so you know where we're coming from, the installations that we represent being Wall-Tite and Atlas Polyiso. So the agenda, we'll talk a little bit about what I mean by fuss. Sorry, I don't have a wireless thing to advance this with, so I'm going to be stuck back here. So a bit about sustainability, the report card, and then talk about air barrier materials versus air barrier systems. And I think this is a very important part of the discussion because it's becoming more and more of an issue with the new building codes and such coming into play. And installations and how they compare, and some examples of wall systems and some takeaways. So I'm kind of an impatient person, don't like a lot of complicated things. And what I've been seeing is as the code becomes more restrictive, if you will, when it's putting more and more requirements on the design community, I see more and more layers ending up in a wall system, and they become very complicated. So I tried to find a really complicated wall system picture, but the best I could do is come up with this rail picture, just to give you an idea of what we're talking about. So that's what I mean by fuss: systems that have too many layers, that are too complicated, and also some exotic materials which have merit in their own right, but may not have very extensive use in the mainstream construction. Things like straw bale, denim insulation, aerogel, which is a R10 per inch kind of a blanket, and VIP, vacuum insulated panels. These are good technologies, but they're kind of niche technologies. They're not really mainstream technologies. And of course, eco-bling is just another little pet peeve of mine that I had to put a slide on. You have inefficient buildings with a lot of glazing, with a couple of windmills on top. So I like the quotation here from a professor of engineering in the UK, talking about eco-bling and how it's attached to poorly designed buildings. So sort of, it's kind of contradictory, or a bit of a paradox. Just to sort of lay out the ground here, in terms of how much energy is consumed to construct and operate buildings. It's quite extensive. It puts a lot of pressure on the design and construction community in terms of sustainability. So 1/3 of all the energy is going into our buildings one way or another, either constructing or operating. And of course, there's lots of things we can do to produce energy that are better than what we've been doing in the past. Renewables, like large-scale wind farms and solar. But at the end of the day, and for the rest of this discussion, we're really talking about conservation and how to conserve energy. That's what this really revolves around. That's recognized as the best way to lead to sustainability, is basically to start by conserving energy and then look at how you're producing the energy. So the nice thing about energy is that you can easily measure it. Some people will say, you get your bill in the mail, you have meters for all sorts of things. So you can figure out how energy efficient your building is today, and you can compare that to how it is after you retrofit it. Or you can compare one new building with another that's of similar size. This is quite telling, and I use this in a lot of my presentations just because sometimes we think and feel like we're doing the right thing, and unless you actually measure it, you really don't know. So when you look at this chart, it was data that was compiled in 2005. The printing's a little bit small, so I'll walk you through it. It was compilated in 2005, and the red line basically just shows you sort of the average of all these years of building vintages. Along the bottom, you have buildings built before 1920, and over on the right-hand side, buildings erected in 2000 to 2004. And you can see the energy use line is pretty much flat. You would think that this line would be going down. In fact, in many years it went quite high. And you might be able to correlate this with how we used to construct those buildings in the 60s and 70s and 80s. We are sort of slowly improving, but it's, at this rate, it's not a fast enough rate to be sustainable. So I give it a grade F. That guy does. In terms of what's reducing our sustainability, things that we need to pay attention to, and things that the building code is paying attention to now as well. Of course, thermal bridging. And things like framing, brick ties, any discontinuity or penetration through the envelope, all these can reduce your sustainability. And they can reduce it anywhere from about 10 to 50% or even more, depending on how much there is. And that wall I show is really not uncommon. I mean, we're using more and more steel in construction, and more of it is penetrating from the inside right through the envelope. And of course, the pet peeve of most building science people these days is the fact we use far too much glazing. And you sometimes wonder if it's really practical or needed because, how much daylight do you really need in a 500 or 1,000 square foot condominium? With floor to ceiling windows, it certainly looks dramatic, but it's very inefficient. And one thing about glazing that I don't see in a lot of presentations is that if it's rated at R3 today, it's only going down from there. Typically, thermal pane windows and sealed units are good for about 20 to 25 years, and then they're basically the gas is replaced with air. So if you start out at R3 or 4, that's great. That's about as good as you're going to get with common glass, but it's only going to go down from there. Dr. Straub allowed me to use some of his slides. He's someone I try to follow quite regularly. And you can see here some of the R values that you get from typical so-called modern walls. So the R2 wall on the left looks pretty modern, pretty interesting, but there's a lot of things happening there. A lot of glazing, a lot of thermal bridging. The wall on the right has less glazing, more spandrel glass with some insulating value, but still R3. And the old building at the base is R4. And it looks like it has about 25% glazing and probably no insulation inside the solid masonry. So it's actually outperforming these so-called modern buildings. So this is the quiz part to make sure everybody's still with me here. Anybody want to make a guess as what the overall R value of a wall would be if it's 50% R20 wall and 50% R2 window? Pardon me? Around 10? R3.6. So you would think it would be an average. That would be the obvious thing to check, right? I kind of thought that too. But through the testing, the heat will take the path of least resistance. So it's going to find its way through those conductive materials, those thermal bridges, the frame of the window, and such first. It's going to go there first, and through the window itself. And then it's going to seek out the higher R value area. So it averages out to R3.6. And similarly, if you think, oh, I'm going to reduce the glazing significantly, go to say 2/3 R20 and 1/3 R2 roughly, you end up at R5.3, which doesn't sound like a lot, but compared to R3.6, it's about a 50% improvement, which is significant in the terms of energy use. So what I say to all architects is reduce the glazing. So I don't know if anybody knows what that building is, but it's a prison in, I believe it's in downtown San Diego. And I think I'd rather be in the building on the right, even though it's less efficient, but it gives you an idea of what you can do. So the other aspect of sustainability that is being addressed more and more now is the air leakage of buildings. And again, we're talking about real air leakage of real buildings with windows and doors that are constructed by real contractors. So the energy consumed by air leakage of all the energy used to operate the building is 60%. So if you can get that air leakage down to a controlled level, to a reasonable level, then you're going to save an awful lot of energy. You have an opportunity to save 60% of your energy use right there. And of course, the cost of air leakage is much higher than the energy cost. You don't have to go very far to see new buildings with swing stages on them, new buildings where they're gutting suites, taking drywall out that's moldy. In Vancouver, you've all heard of the condo issues they've had there. And a lot of that was driven because they use a lot of wood frame. And when this heat and humidity and air escape the building, they're going to deposit moisture in the wall system. And that's going to cause rot, mold, discomfort issues, and all sorts of other aspects. But it's going to be costly to repair. So we're all human, so we really only start to comply with things when we're forced to. I don't know if you remember the Red Green show, the man's prayer. If anybody remembers that. You only really improve if you have to. So the building code basically forces us to improve. So there's other things that might help us to improve, things like financial incentives from the government, lead publicity, for marketing purposes if you're a large corporation. We're not going to talk about those things. We're just going to talk about the building code and the history of it and where it's going. So the building code, when it first came out, was really focused on health and safety, trying to make sure that the buildings had a certain level of structural strength, a certain amount of health and safety built into them. And then we started talking about basic R values in the 60s and 70s, perhaps even in the 50s. 1985 is when I was really sort of heavily into the business of air barriers when the code changed. And I was actually involved with air barriers in that very year. So the code started to say, thou shalt put an air barrier in the wall. Prior to that, it said you needed a vapor barrier and insulation. Didn't really talk about air barriers. In the 90s, we've increased the R values. 2012, which is, I say, a new era and a really challenging year for a lot of designers and owners, because now you've got to incorporate, or you've got to meet the SB10 and SB12 requirements for R value and performance, which are pretty significant changes from the past code. This is now taking into account the effect of thermal bridging, the effect of convection. It's requiring things like CI, continuous insulation, CI, and also forcing us to do a lot more energy modeling. 2015, the code there is going to start calling for air barrier assemblies or systems. So no longer can you just take a piece of some material, test it, and make that your air barrier and be code compliant. As of 2015, and even maybe sooner in some provinces, you're going to have to use basically a tested system that incorporates all those things you need to build that wall. And I don't know where the future lies, but probably more R value and more significant changes there too. So again, quoting my mentor, if you will, Dr. Straub, we like to break it down. So we're not looking at the cladding here in this discussion. We're looking at what we call the control layers. So you have a rain control layer, an air control layer, vapor control layer, and thermal control layer. So these are the parameters I like to think about when I'm looking at a wall assembly, and trying to make sure that we address all four of those aspects within that wall assembly one way or another. And of course, you can take that wall and flip it over and use most of that information and analysis to analyze a roof or a floor as well. It's going to be a similar situation. So again, on the subject of fuss, if you will, we're talking about systems that end up having a lot of layers in them. So this particular wall you can see has 8 layers when you include the cladding and the interior drywall. And that's because basically they've been just, each layer has one function within the wall system, for the most part. To contrast that, you could go to a system where you have a product that takes care of many functions within the wall system and simplifies it. Now we're going to talk a little bit more detail about systems that, these two systems plus systems that are in between the two that might suit some projects that you're working on. First off, as I mentioned earlier, we wanted to talk about air barrier systems versus materials, and I really can't stress this enough, and there's some important takeaways at the end of these next few slides. So in 85, the code said you must use an air barrier, and it listed off about 20 or 30 products that were air barriers. So drywall is rated as an air barrier. Certain types of insulation board are listed in the code as air barriers. They have a low enough leakage rate when tested as a material to be rated as air barriers. So it's not a hard test to meet. It's very inexpensive to run this test. And it was a good starting point. It's based on the ASTM 2178. And in the newer codes, in the National Building Code, they're starting to talk about the CAN-ULC S741, which is similar to the 2178, but it really adds an element of exposure. So now they're saying, okay, these products are air barrier materials. They're still just tested as materials, but let's see what happens to them when we expose them to various conditions that we're going to find in the field, and then test them again. So that's essentially the 741. The problem with this test is, of course, it doesn't include anything that we have in a real wall. There's always window openings, brick ties, doors, all sorts of things coming through the wall that aren't accounted for in this test. So it's a good starting point, but not much further than that. Beyond that, there's the system testing, and this is pretty typically 8 feet by 8 feet, the sample size. It includes many different things: openings, penetrations, transitions, a lot of the details you would find in actual wall conditions. You can see on the right-hand side some sample walls being prepared and actually some being insulated. So the thing with the system test is it's the manufacturer's call as to what substrate is tested. So it might be tested on just block or just steel stud and sheathing. What kind of sheathing is on the wall? These are all variables that the manufacturer has some say in, and they have to make a choice as to how they test their system. Also, the thickness of the materials that are being applied, where they're being applied in terms of the level of detailing. All this is a variable that needs to be taken into account and decided on by the manufacturer and then tested by the lab. And then once they decide on those parameters, those variables, once they confirm what they want to do exactly, then they would pick the testing method. Of course, in Canada, we'd probably jump right up to the CAN-ULC S742, which is the air barrier system or assembly test. It's derived from, I believe most of these were derived from the CCMC air barrier system listing and report, or air barrier technical guide that was established back in the 90s. That's where I believe where the ASTM 2357 came from, and the CAN-ULC S742 came from that. So the American test doesn't have any conditioning requirements in it. The Canadian test has conditioning requirements in it, and then the CCMC guide has more extensive conditioning and has more quality assurance to make sure that what was tested is actually what is being used in the field. So the challenge with systems that is going to face specifiers is you can't simply call up a product and just include it by name in the spec and talk about generally how it's installed. You have to get into more detail. And if you spec 2 or 3 products for a particular application that are all 3 air barrier systems, one of them might require more extensive detailing than the other. So you're going to have basically 3, you're going to have to refer to the 3 manufacturers' tested assemblies within the same spec. So it could be kind of complicated. For instance, to give you an example, if you test something like a spray foam product on sheathing that is over steel studs, one manufacturer might test it without putting any treatment on the joints between the sheathing boards. Another manufacturer might require extensive detailing of those board joints. If you're going to spec those 2 products in the same spec, you need to capture that in the application part of the spec. Because the one manufacturer doesn't need to do it, they've proven that they can pass the test without it. The other manufacturer had to test with it. It has to be specified that way and installed that way. So it's not a, it's a bit of an unlevel playing field, you might say, but those things have to be taken into account and transferred into the drawings, into the specs, and then ensure it's built that way. And of course, systems are going to require a lot more inspection than what we're currently doing on building envelopes. Pardon me, I'm losing my voice here, a bit of a sore throat. So the, in respect to thermal bridging, again, it's quite an extensive, quite a large source of heat loss in buildings. You can see here, this building is basically lit up on the thermographic scan. There's a lot of red, yellow, and green. We do things like put balcony slabs that continue on right into units as the floor of the unit. Excellent ways of transferring heat to the outside. The device on the right-hand side is something that we've seen being used. It's from Germany, I believe, called the shock system, and it's a way of isolating a balcony from the interior slab, thermally isolating it. We're not involved with that, but I have heard it's quite a good product if you're looking for a way of isolating balcony slabs. Spandrel panels in curtain wall and window wall systems. Again, if you've been to any of the presentations by Intermodal and others, you will find that it's very hard to meet the SP10 requirements using typical spandrel panels with, even if you increase your insulation thickness to 5 inches, because you've got so much metal and so much thermal bridging happening around that 5 inches of mineral fiber. So you might have to supplement that with other insulations inside. So the building code essentially is taking into account some of the values that ASHRAE's known of for many years. This chart has been around for, I would say, about 9 or 10 years, more or less. And this information's been known for that long. It's ended up in our code in the last 2 years. So you can see basically what we're saying here is if you use steel framing and insulation between the studs, you put the studs at 16 inch on center, which is the circle at the top, and you think you're getting an R21 because you're using about 6 inches of insulation. Your actual R value is going to be about R7.4. Okay, so this is because of the effect of the thermal bridging of the studs at 16 inch on center. If you spread those out to 24 inch on center, you end up with R9, but you still have a greatly reduced R value compared to the published R value. So that's where what the code is starting to recognize. Another similar discussion is in the ASTM 1365, which was done with Morrison Hirschfield. And if you Google that, you'll get the full report. It's available for free online from a number of sources. MH actually has a summarized version of it that helps you to kind of get a quick understanding of what the report's about. And there's a similar report on spandrel panels and the balcony slabs as well on their website. So what they're saying here is if you use vertical Z-girts that go right through your so-called continuous insulation on the outside of a building, you're going to lose a great deal of the effective R value. You're going to have a greatly reduced effective R value, pardon me. If you use horizontal Z-girts, it's reduced again, and mixed Z-girts reduced less, and then intermittent clips. We'll just quantify that. Sorry, I don't have a pointer here, but you can see the black line we're looking at. And if you follow R25 at the bottom, sorry, if you have a theoretical R27, if you use vertical Z-girts, it reduces it to about R12. So you're losing well over 50% of your original R value. If you go to horizontal Z-girts, you end up with R14. Mixed Z-girts, which we thought would actually perform quite well, you end up at R17, which is still out of 27, is quite a reduction. And then if you use intermittent clips, and I can show you some examples of those, you'll end up at R20, effective R value, for published R value of 27. So again, we really shouldn't be seeing exterior wall systems right now with exterior one-way Z-girds, whether they're horizontal or vertical. We shouldn't be seeing that. We should be seeing intermittent clips at least, or possibly two-way Z-girds. So on the show floor, you'll see a number of thermal clips. I've seen 3 or 4 today already, but this happens to be the T-clip by Engineered Assemblies. It's one that I've seen quite a bit of. There's others by Flynn and ETG and other companies as well. Currently involved in a project where we're actually using these clips in kind of a different way, creating a bit of a different system. We're actually furring out the exterior sheathing on horizontal steel that's held away from the studs by one of these thermal clips. And I'm going to show you a little bit more on this in a few slides ahead. It's a way of thermally breaking the sheathing and the exterior from the interior. So there's a bit of a schematic of it with a T-clip. So instead of putting the sheathing between the T-clip and the stud, we basically move the sheathing out to the outside, so it's right behind the cladding system. This way we can spray foam in behind and create a thermally broken, furred out sheathing type system. So we'll show you a little bit more on that in a moment. So insulation, we're talking about different types of insulation and what function they can perform. And I don't think it's any mystery that fiberglass and mineral fiber can perform basically one function, thermal control only, okay? So that's what they're providing. Now the nice thing about these products is they are non-combustible. Most of them are. When you're installing them between studs, there are potentials for poor installation, bringing the R value down significantly. So there's been a number of studies that if you have rounded corners and the product's not installed just perfectly, you're going to lose quite a bit of the R value. So they show published R value of 19, perfectly installed are 17, commonly installed with some rounded corners and a few gaps here and there, you're going to end up with R 13.7. So you lose about 28% of the R value. So you have to be careful in how these things are installed between studs if that's how you're using them. Extruded polystyrene, rigid, it's a plastic foam. Like many plastic foams, they're all combustible. It provides thermal control only. Now, even though the product has low vapor permeance and probably could be rated as an air barrier material, there's very little testing on them as an air barrier system or as an actual vapor barrier to actually be the deemed vapor barrier in a wall system, let's say. So they're really relied upon as thermal control only. And we talk about global warming potential. You'll see that pop up a few more times here. And I think you'll hear from some of your architectural consultants and your owners, they'll be looking for more low GWP products. And extruded polystyrene is a product that has a high GWP currently. The North American version of it does. The European version is low because they use a different blowing agent. But in North America, they're still using the older blowing agents and it has a high GWP. Things that can affect the performance of this kind of board, and any rigid board for that matter, if you leave gaps behind the boards and the substrate, if you leave gaps between the boards, then it's going to lose quite a bit of its R value. There's been some studies, very old studies from 1962 even, where they state you can lose about 40% of your R value with small gaps between and behind the boards. So it's pretty significant. So what we suggest is in situations like this, if you're going to use a rigid board, use a full bed of adhesive, use adhesive between the boards. You want to make that continuous and as monolithic with the substrate as possible. If you allow air to move around these boards, they're not going to work as well as they should. Expanded polystyrene board, which again, I think you'll see a resurgence of, has very low GWP. Still based on polystyrene, but the blowing agent is air. So it has a very low global warming potential. And it's been around for a very long time. It is combustible still, based on plastic. And again, it provides thermal control only in typical installations. And it's a bit of it's a product that's really not used as much as it should be in Ontario. I'm not sure why, but if you travel west, you'll see a lot more below grade applications of expanded polystyrene and roofing applications of it as well. In Ontario, we don't use it that much that way, not just yet, but I think you'll see that grow. And of course, it's the primary insulation used with the EIFS systems, so it's quite stable. Polyisosanurate board insulation, again, a rigid plastic board made out of polyiso, which is very similar to polyurethane. It's rigid, has a low GWP because it's made in a factory. It's made with a pentane blowing agent, has a low GWP. It's combustible, as I said, all plastics are, and it provides thermal control only. That's what it's being used for in typical wall applications. Open cell spray polyurethane foam, again, low GWP. The blowing agent is air and water, essentially. Again, combustible. Now, it can provide thermal control and air control, but you need quite a thickness of it. You need about 6 or 7 inches of it to be a reasonably effective air barrier. So it's somewhat of an air barrier. It will control air somewhat. Closed cell spray polyurethane foam. It does actually, it's able to accommodate all 4 control requirements. So rain, thermal, air, and vapor control. It is combustible, and there's some examples of where it's used between studs and also in a monolithic layer as a cavity wall insulation. Just some other asides, insulated metal panels, which actually are cladding themselves, provide all 4 functions as well. The most common is actually filled with polyisosanurate or polyurethane, so it's going to give you similar properties to polyurethane, plus the fact it has metal on both sides, so it's even a little bit improved, and it is a cladding and an interior finish all in one. So again, you'll see more uses of insulated metal panels in the future, I think, because they create that envelope very quickly and inexpensively. And you can get non-combustible, which would be mineral fiber filled, or combustible, which would be polyiso or EPS filled. And exterior insulated finish systems, EIFS, again, you can prefabricate it or apply it on site. And again, these can provide all 4 of the control mechanisms that you need in a wall system. And they can be non-combustible or combustible, similar to the insulated metal panels. They can be insulated with EPS or mineral fiber insulation. And we just showed the prefabricated. We're involved with a product line that's prefabricated, so we believe in creating EIFS in a factory and erecting it on a wall as a panel, as opposed to site applying. So those are all prefabricated EIFS jobs. So we're going to talk about some typical wall assemblies. Any questions so far on the cladding, on the control mechanisms, or on the other information we've put forth so far? So we're going to talk about a kind of a traditional stud wall where you have just no continuous insulation, sort of your standard developer wall or residential wall that we might have seen in retail or tract building of homes. So you have your stud, whether it's wood or steel, your cladding, or sorry, your exterior sheathing board, pardon me, some kind of rain control membrane, sheathing membrane, fiberglass or some type of bad insulation in the stud space, and your cladding. And then your interior vapor barrier, which was meant to act as your air barrier as well, and then drywall. So this wall is still being used, but its days are somewhat numbered because there's no CI in this wall, no continuous insulation. And especially if you're using steel stud, I believe right now it's very hard to comply with code unless you use CI. In a wood stud wall, we still see residential walls being built this way, but in I think 2017, the code's going to change in residential to require more and more CI as well. So it's going to make builders change the way they do this. So as I said, it's low cost, it's compact, so it's relatively thin, no CI, and it has a limited effective R value. You're limited by the 5.5 inches of space you have in the studs. You can make a bigger space and put more insulation, but it's only going to increase your effective R value so far. So you have an effective R value limitation of about R13 or 14, a published R value of about R22 to 24. And using the poly on the inside is a really poor location to create an air barrier because you're trying to make it continuous. And it's broken up by interior walls, electrical outlets, all sorts of things. So an improvement on that would be to install the studs, install your sheathing, install CI, which could be semi-rigid mineral fiber, could be polyisocyanurate, expanded or extruded polystyrene, or spray foam for that matter. If you need it, depending on the insulation you're using, you need a sheathing membrane. With some things like polyiso, you can tape the joints and create a sheathing membrane out of the panel. You can use fiberglass insulation in the stud space, rock wool. Again, you could use spray foam, low density or medium density spray foam. Again, depending on the insulation you're using, you might or might not need an interior vapor barrier. If you're using spray foam in this case, closed cell, you wouldn't need it. But if you're using the other insulations, the open cell products, you would. Your interior drywall and your exterior cladding. So this wall is much improved because you've got CI now, and you're going to reduce your thermal bridging quite a lot. Even 1 inch or 2 inches of CI is going to make a huge difference here. You've got a potential for a second air barrier by caulking and sealing the interior poly, but you can achieve a really good a better air barrier on the outside of the sheathing, where it's more easily made continuous. It's still somewhat of a complicated wall, though. Complicated from the point of view of having to work on both sides of the wall to construct it and to insulate it. Also complicated from the point of view of the fact that you have low permeance insulated sheathing on the outside, open cell bat type insulation in the middle, and then another vapor barrier inside. So this wall, it is allowed by code, and it can be done and it can be successful, but you have to be aware that you have a 2 vapor barrier situation, and you have to be careful about your ratios of the outside insulation to the in-stud insulation. And there's a part of the code that talks about that. And if all else fails, you can always run a Wolfe analysis on your actual assembly. Yes? Oh, if you were to use insulated, if the insulated sheathing was polyisocyanurate or extruded polystyrene, it's a low perm sheathing, right? Less than 1 perm. Yeah, so that's going to constitute a vapor barrier, and then the poly is used on the inside, so you've got the 2 vapor barrier situation. The foil face products are less than 1 perm. The coated glass face products are just slightly more than 1 perm, but it's not like an on-off situation. You know, it's a rate, right? So your rate is 1 perm or 1.3 perms. It's still really low. So I would still consider it a dual vapor barrier situation. Now, if you use semi-rigid mineral fiber, that wouldn't be an issue because it's not constituting a vapor barrier. So again, we deal with spray foam quite a lot, so we'll show a few assemblies of that. So you can apply spray foam on the outside of the sheathing. You can spray foam in between the studs as well on both sides of the sheathing. We do this quite commonly. Install your interior drywall and your exterior cladding, and you're basically done. So this is, again, a wall that's not very fussy. It's very simple. The spray foam is acting as the rain control layer on the outside. It's giving you the IC and thermal control, and it's also controlling the air, because the permeance of things like closed cell spray foam, they're rated as air barriers, and sometimes air barrier systems, depending on the product. So you have minimal condensation potential because it's all closed cell, all within the same plane. We've had these walls analyzed through a Wolfe analysis. They've come out very good. We've been doing this kind of thing for well over 10 years now, and it's worked quite well, even in high humidity situations like public housing and things like that, rec centers. Oh, sorry, what was that question? The R value of that wall? Well, the R value of the continuous part on the outside would be close to what we publish because there's very little thermal bridging going on there. The R value of the part between the studs, if you ran a modeling program through it, you're probably going to be getting about 50 to 65% of the published R value because of the effect of the thermal studs. So yeah, you won't get the full published R value from it, the in-stud portion. So that's what it would look like. You have a couple inches on the outside and maybe 2 inches on the inside between the studs, and that and then the drywall goes over it. Oh yeah, the metal studs are much worse. Yes. In terms of the reduction of R value, that table that I showed you, the ASHRAE table, that's all about metal studs. Wood studs, the reduction in the R value would be significantly less. So instead of losing about 60%, I'm just ballparking it, you're probably losing about 25 to 30% with wood. Another sort of option, and this is that wall we showed earlier. So you have your studs, your wind-bearing studs, typically. One of those clips, those thermal clips, could be the T-clip, the Flynn version of that, the other versions. Some kind of clip to isolate, thermally isolate. Some kind of a horizontal hat section or Z section going across the wall. The exterior sheathing. And then to maintain continuity and create a drainage plane, you would put a breathable membrane on the outside of that sheathing. We can foam in and around all of that by applying from the inside of the wall, and it would work its way around all the thermal clips and everything else. Interior drywall, and then the exterior cladding. Now, I show brick here, but in most cases, when this wall's been used so far, and it's relatively a new concept, the cladding has been more like an ACM panel or some kind of metal cladding, something lighter than brick. You could use brick with this, but you'd have to somehow structurally support it back to the studs through all that whole system. So it might be a bit more complicated. I meant to change that brick to ACM or metal. That's what we see typically. And that's the slide I showed earlier. That's a job being done just outside Victoria in BC. It's a high school. And you can see the horizontal steel. I'm sorry, the photograph's not much better, or not very good, rather. It's not very clear at showing everything, but you have the horizontal steel. There actually is a metal clip back there, a thermal clip, and then you can see the vertical studs. And then the spray foam is being installed from the inside. Yes? The 2012, in most of the options you have for SB10, they call for continuous insulation. I think over all the options where you have metal framing, you need to have continuous insulation. And in the residential code, it talks about it in SB12, but I think in SB12 you have about 15 streams, and a few of them call for continuous insulation. Yeah. Oh, that's glass rock, Certainty glass rock. Yeah. That's how bad my slide is. You can't even read the logo on it. Sorry. Some other options could be a block backup or steel stud. And this is really the ultimate wall if you have the room for it, because it is a wide wall. Put your exterior sheathing, a continuous air vapor barrier membrane on. In this case here, we show something that it's not plastic foam. It's probably a semi-rigid mineral fiber, let's say. And then your interior drywall and your exterior cladding, whatever it might be. And this is a very good wall, but it can be very thick because the mineral fiber has a lower R value. But it is non-combustible, and that's required by code in some applications. So that's kind of an ultimate wall if you need a non-combustible system and you have the space. And the other option, of course, is to use the studs, exterior sheathing, transition membranes, so membranes where you might anticipate movement, expansion joints, control joints, and then the spray foam being applied from the outside, and then the exterior cladding. So again, a very simple wall, still fairly wide because all your insulation is on the outside. You're not putting anything in the stud space. Really the ultimate wall. This is what we see on, of course, schools, hospitals, places like that, where they've got the budget and got the space to do it. And this is really my starting point if anybody asks me for a suggestion on a wall is to go all continuous insulation all on the outside. So your air and vapor barrier are in the same plane. Your continuity is good. It's relatively easy to make it continuous because you're outside of the sheathing. It details well with adjacent materials like curtain wall and other windows and such, doors. And it's relatively fast to install. That's one thing about spray foam, it is quite fast and less costly than some of the other options. But it is a fairly wide wall. There's an example of that's actually a hospital, and you want to talk about brick tie frequency. There you go. So you can see there's a lot. It's not even a tall building. I'm not sure why there's so many brick ties, but retrofitting, of course, most of our buildings are existing. Of course, the new construction is one thing, but we really need a strategy to deal with existing buildings. And there's a number of ways of doing it. I've just shown one example that we've done many times. And this could apply also to the inside of spandrel panels in curtain wall systems. We've done it there as well, where you set the steel framing back at least 1 inch, preferably 2, from whatever the substrate is, masonry or spandrel panel backpan. And then you can spray foam between and behind the studs to create a continuous layer of insulation and also an air seal. And then by doing this, you maintain it's relatively easy to maintain continuity. And it's not for every wall, not for every historic building. Historic buildings have to be looked at in more detail than new. If the exterior masonry is in bad shape, you don't want to start just foaming to the inside of it. We need to remediate the exterior of that wall. We also have to understand what's happening in the exterior wall, how friable it is, how sensitive it would be to freeze-thaw cycles. But we do see this a lot on spandrel panels now, and it's becoming more of an everyday application for foam. That's a very good question. I was actually going to create another slide showing a drainage layer between the foam and the substrate, which has been done as well. So if you had a situation where you needed drainage there, you felt you wanted to accommodate some drainage, then you could incorporate things like a dimpled plastic foundation wrap first, and then foam over that. The thing with drainage is, though, if you create a drainage plane there and you're actually expecting that much moisture, then you've, of course, got to detail a way for that moisture to get out of that space. So you've got to start drilling through your masonry, creating some kind of pathway for that moisture to escape the system. And that's really the challenge. But we have done it with and without a drainage plane. I'd say 95% of the jobs are just like that, though, where they're directly to the back of the masonry, if it's multi-wythe masonry. If it's a single wythe of brick, we would tend to favor putting a drainage plane. Exactly, yeah. Yeah, we've been defrosting, and the way this building operated before it was insulated is basically it's like one large defroster. No matter how cold it got outside, the masonry was always above zero, or close to at least, because the heat from the building was escaping into it. As soon as you start insulating, you're isolating it, and you're making that exterior go through more and more freeze-thaw cycles. So you do have to be careful with this. You can't just go ahead and spray every building and hope for the best. You have to analyze each building on its own. Again, we can help with that a bit. Building consultants are pretty familiar with it too. I know some of them have done pretty extensive studies on this sort of system and how they work. And they can let you know if they think you need drainage systems or not within them as well. So I thought I'd go easy on you and not keep the presentation going too long, since it's the last one of the day. So some of the takeaways. I just hope you kind of leave here thinking about control layers. So next time you look at a wall assembly, sure, you're thinking about R value and all that and how it complies with code, but think about control layers. What are those layers in the wall doing, and that you want them to do, and what might they be doing that you don't want them to do, like the double vapor barrier situation. You can't control what they'll do. If they're low permeance, they're low permeance, and you have to know that going into the design and analyzing it. OSB is it's very low in permeance as well. Code compliance, again, just trying to give you a few tips on where the code came from, where we're at now, and where it's going in terms of assemblies. Effective R value versus published R value. And this is where I'm like the bad news bearer, because you thought you were getting R30 or R40, and I'm here telling you you're getting R10 or 20. So sorry about that, but that's the reality. Thermal bridging and continuous insulation. Again, I think it's just good practice to have continuous insulation. The school boards and the hospital builders have been doing it for 30 years. And you know, they really work well in reality. Those walls work very effectively with very little insulation in many cases. 2 inches of extruded was kind of the standard on schools for many years. R10, it's not very much. And then thermal bridging of all that steel, the Z-girt systems. Again, hopefully leave here knowing that, you know, using one-way Z-girts, whether vertical or horizontal, is just not a good idea. Or relying on insulation between steel framing is not a good practice if there's no CI outside of it. Air barrier systems versus materials, again, looking at products first, and then trying to understand if they actually are a bona fide system. The code's going to require that soon enough. And also that there are some proven options out there. Some of the wall systems we showed you have been used for many years. The one with the thermal clip is relatively new. We've done a few jobs that way, and we're trying to get some feedback from the field as to how well they work. I would like to see a thermal clip job with a masonry veneer, a heavy veneer, to see how that works and how that comes together. So we can look at all the wall sections on here and pretty pictures, but it comes down to how can these things actually be built in the field, and are they practical? So I appreciate your attention, and sorry about the scratchy throat, but if you have any other questions, I'm here to answer them.